Hi, and welcome to another exciting edition of Shader Development. My name is Nate Nestler, and this is for Hyperactive Studios. Okay, so the last time we looked at the glow shader, but today we're going to be looking at another thing you can do with that wonderful filtering process where we actually can make it go cartoonish. Or this is what's also referred to as edge detection. Okay, so essentially we get in this kind of shading look to it. And this is using a Sobel edge detection algorithm. It is not as accurate as some other methods, however, it is fast. So that's what's really nice about it. And the results are pretty cool. Let's face it, that's very cartoon-like and it's very cool. So let's look at the math behind this, what's involved. It's not bad, actually. This is, I have to say, some of the image filtering stuff is some of the easier algorithms out there compared to light models and things of that nature. We'll just have a look at that and what's going on here with all this and how this breaks down and how to implement it. Alright, so let's go through the theory first that makes sense for breaking this down. Okay, so if you last recalled, we went through this whole thing here where we had our image filtering for our basically for the whole glow blur operation, and in this case it's a blur operation. But you can see we have this weighted pixel 3x3 grid, more or less, and we're manipulating the lookup values here by adding and subtracting horizontally and vertically. Okay, with that, and then we average the elements. It's kind of like that, but not quite the same. If we look at Sobel algorithm, Sobel operator here, it allows us to do this image detection, and Wikipedia does a wonderful presentation of this. Here's an example of an image here, and then the Sobel edge detection algorithm placed on it, and then we get this result here for it. That looks really cool. Basically, we just need a breakdown of how this works. There's other algorithms besides Sobel that you may be of interest in. And if you look at this here, but you'll see Kroon, I hope I'm pronouncing this right, Shar here, and then we also have Frid and Farid, I'm not sure how you pronounce it, and then Samanseli, I hope. That's how you pronounce it. I'm sorry if I massacred your name. And you can end up with some better results with some of these here. So by no means do you have to confine yourself just to the Sobel algorithm. You can actually change up these algorithms and try some of these other algorithms if you so desire. And here you see some different results coming from that, which is pretty cool. And we can get some very different results with this. But anyways, let's just look at the Sobel algorithm and see what we can do here with it. Okay. And with that, there's two passes done generally, a vertical and a horizontal. We only do a horizontal pass in here, but generally you would do both. Of course, it takes more time to compute both, but if you're just trying to do a quick and dirty Sobel, you could do it in one direction, which is kind of what we're doing. So, well, I say horizontal. I really meant to say vertical. I'll have to change that in the code. Okay, I'm getting them mixed up. So this is your horizontal detection, and then this is your vertical one here, apparently. Yeah. So, and this manipulates the pixels in order to determine the detection along one edge. And that's exactly what we do. And then we do basically something like the distance formula down here for its magnitude. Yeah, for the gradient. And that's essentially how it works. Okay, so as a better explanation here, let me explain this a little better. Basically what we're doing here is you have a gradient value, and then you're seeing the same color here over and over again, and then you get to an edge where you get a different color value, it changes. You're then putting this either into a 1 or a 0 type operator what I mean by that is the moment you go over one value here, it can either be a 1, which would be white, or a 0, which would be black. And that's how we're getting this set up here. And that's how we're drawing the lines and such. In this case, we have a black background with white lines, and that looks cool. You could do it the other way around, where you have a white background with black lines. It just totally depends on how you want to switch it up, as far as that goes. But we only have 2 possible variances, only 2 possible colors, either black or white. And based on the gradient range here, we determine whether or not it should be black or white, and that determines an edge. So when we get this big color shift between the two based on some threshold, then that will allow this to detect an edge. So you can see there's a big variance here between this white here and this gray here, and because of that, we can detect that edge. And this is not a precise science, because you could have different variances, and it becomes a question of which gray is the magical gray for doing the detection, or something of that nature, or which, where do we cut off that value for what would determine an edge type thing. And that can be tweaked or driven, so on and so forth, as far as that goes. So with that is essentially what we are doing here with these values. We're computing this among the corresponding pixels around the center pixel here, and this, so you can think of these as pixels here, and then you're determining, hey, does this fall within inside of a variance of being an edge, or is this not, for gray, for a color change. And basically this pushes the values one way or the other, to where they're one extreme or the other extreme of the scale of color. So in this case, as you can see, this white here became one extreme of just black, 0, and then as we move to this other extreme here, we detected that with this, because we're able to get the edges detect from here for the pixel where that change occurs here, and we're able to determine that that is an edge, and so we colored it a different value, which is white. Essentially, that's how it works. It's kind of hard to explain it any better than that, I'm afraid, from my standpoint. I mean, you can get in here and read this thing in detail. It'll get into a more technical explanation of it. When we start talking about the normal direction of the vector of the gradient, as far as that goes. I'm just trying to speak from a non-technical standpoint here about how it works in basic terms, and breaking it down to where you can make a better sense of it. But essentially, that's how it works. Okay. Yeah, and in here he's talking about doing the vertical edge here was darker on the right-hand side with this. They're using an A tangent. Now we use dot product instead, and that works great. And then they use a tangent value here for doing it. So we have 2 vectors. We just take the dot product between the 2 vectors, and we get our result that we're looking for. And that worked out fine for us. So basically, it is the same algorithm. I really wish this would stop doing this. Same algorithm, and we have control over it. Now I can come in here to my values here. I can change the thickness or the detail level here. And you can see a difference here and how you can control the look of this, which is pretty cool. I gotta say, that is pretty neat, that you can go in there and just tweak. We can also play with the step size. Just like we had a step size beforehand, we have a step size this time, but it's a little different than before. So this lets us say over what variance of the textiles are we sampling from, and of course you can see a big difference here based on the range of pixels we sample for, or should I say, textiles. As we decrease that range, it samples less and less than if we increase it. So it's up to you what it is that you want to set it to, as far as that goes. As a special note here, I did go ahead, before I applied this shader, I went through and I just took the default material and applied it to the plane, to the teapot, and then also to the sphere before I applied this cartoon. Remember, this is a screen space shader, so it does need something to work off of. So this gives me light shading variations here. Now, if I had done something differently, if I had gone in and just did a single color, for instance, in here, I would have quite a different setup as far as that goes. And then basically I could set that up to where, hold on a second. If I wanted to, I could create another shader that honestly just returns the color like that. And whatever I apply this to underneath the hood, so on and so forth. So there's a problem because it's white. It's still a problem because it's white. So probably not enough definition there in order to cause an edge detection. So, okay, never mind. There it is. But when it's white against white, it's hard to see. So you can use this to do an edge detection. Of course, you're not getting any more shadow values here or anything like that. You may find Lambert. It might be a better choice for yourself as far as that goes. Solid colors may be what you want. I don't know. It depends on what you're going for. But you can see, depending on which algorithm you have applied to this, because remember, this is a screen space effect. That depends how well it can pick up variances here for your edge detection. Of course, that makes it pretty extreme for your edge detection there with just a single color like that. But then also realize you're not going to get any kind of variation if they overlap because there's no shading involved. So you got to take that into account when you're making one of these. If I have, however, this default material here, notice we get shading, and that is we're getting specular lighting and all this stuff, interactions are occurring. I'm trying to remember, does it have a default Lambert in here? It does. So if I were to do a default Lambert in this thing here instead, let's take that Lambert and apply it to it, preferably without the texture. Well, there it is with the texture, and you can see the drawing results you get with this, and they're pretty good. You can see as we go into darkness here, total darkness, it just kind of draws out into nothingness for the lines, but we're actually getting those details from the texture. And that's pretty cool. I think that's pretty neat, actually. So here you can see the actual render here, and here you can see the other result. And you see the difference we're getting between a specular valued here and not. If I didn't want the specular value on here, I'd simply just set these here, like so. And then you can see the results from that. You can also have a like cubed background here, and it would also draw it for the drawing lines and things of that nature. So here it is with textures versus not textured, and with the Lambert shader. And then here now we're getting a very solid look to it without the change in the specular. So really, honestly, it depends on what you apply to it for a shader, as depending on how it's going to draw it, because here we're seeing the result of a specular shader getting picked up by that Sobel edge detection algorithm. So totally depends on what you want to do here. So there we're getting our specular value again. So I'm just going to leave one with the Lambert and one with the Fonk so you can see the difference between the two for a teapot, and with the texture on it. It's kind of cool. Alright, so anyways, I'll shut up about that and just move back over here to my screen space edge detection shader. Okay, so back over in here, we can see a particular setup here. And what we need to do is, what I did is I copy and pasted my whole glow shader from before, and I just called it screen space cartoon edge detect. So I copied that, and of course I went to create, and then I said effect, and then I said CGFX, and then I said empty, and then I named it, and I named it, you know, post cartoon edge detect .cgfx. And then I pasted in, copy and pasted in the code from the glow shader. Now this is going to change a good bit, just so you know. Note we are using the Sobel algorithm. It's not necessarily the best algorithm, but it's a fast algorithm. and it's not as accurate as some others, but it does yield decent results and decent calculations for your images. So that's great, and that works. So this description area actually for once put a description in of the shader. Aren't I being professional for once? Alright, float script, colon, standards, global, all this stuff's the same as always. Shouldn't have to change any of that. So that should all still be the same. Artistic controls. Well, artistic controls under here, we will have textile span. I changed the name of it, but this is basically the same control we had from before for the whole textiles spanning out, and for sampling multiple textiles when we were doing a range for the glow. So remember, as we brought that slider out in the glow one, let me pull up the code. Where did I put it? Yeah, that one. So basically what I'm saying is you're just going to change this one, glow span. So we're basically changing the glow span. You're going to ditch your seeness and glowness here. So ditch those from the whole screen space glow shader, and you're going to have just your textile span. And then you'll need a threshold. So you can convert, I guess, one of these seeness wherever or glowness, one of them, just pick one of them, and convert that into a threshold here. And that's just going to be a float. Basically, a lot of algorithms use threshold in their name, so just go with threshold. Double H's, of course. I did remember to put const in front of it for once, which is a benefit here. I finally remembered for once to do that. This range helps. It works out pretty good with the 0.5s. You can set it lower here if you like. But don't set it above 0.5. The results look really bad above 0.5, so just 0.5 is great. And about 1.5 to 1.0 is about what you want. And I just did a step size at 0.5. You can make this lower if you like, but you're still going to get jumps in your manipulations. So 0.5 works out pretty good as far as that goes. And then here for your threshold, you also have your UI min, and 0.5 is fine for that too. And UI step of 0.01, and a start with a default of 0.2, and those values work pretty good. As far as clear color goes, this is nothing different. This is all stays the same thing as clear depth, no surprise there. Edge detect detail for the name of this. I just call this cartoon step size and textiles. Really would help if I scrolled down and selected the right. Yeah, and so we get these controls over here. Okay, it can even control the viewport offset if we so desired. I don't remember if I use that or not, so it might be superfluous to sitting around. We do use viewport size. It is very important you have this in here because we will use this without a doubt. So make sure you keep your viewport size hanging around and all that. Don't get rid of it. I just don't recall using the viewport offset. I don't think that's needed. Let me... I tried to delete a bunch of stuff, but I might have forgotten one thing. Yep, I forgot one thing. Alright, so no need for the viewport offset, but we do need this viewport size. That is important. Okay. See, I'll just show you. I'll move it around, and yeah, it's all good. No problems there doing that. Okay, so and then underneath the textures, we reduce some more here. We have our screen space color target texture, and then we have our render stencil depth buffer texture here. So render depth stencil target. And that's pretty much it for those. So again, just limit it down just to those textures, and then you need nothing else. Everything else stays the same as far as that goes. All these are the only ones you need, shall I say. So very simple, and doesn't take much as far as the need for this, because basically we only need the depth buffer, and then we need the resulting final image that we render to the screen space. So not much really there for other passes or anything. We're not going to do multipass. Could. We're not going to, though. It makes it faster if you don't. So if we can parallel compute more processes together, then it's faster than we have to wait for a finish. In times you have to wait for something to finish, it's slower, so you don't want to do that. Okay, so multipass is slower for that reason, because you have to wait for each stage to finish. So you're incurring big slowdowns every time you have to do a second pass or another pass. So you want to keep your passes down to a minimum, because it will really affect you. on your speed. But anyhow, all that said, in and out parameters here, same as always. Just do the VS in like you would expect. VS out, just like before. And then we also have an FS out. So nothing changed there. All of that's the same. On another note, nothing's changed here under our Vertex Shader as far as our main VS. So we're still doing our quad aligned vertex plane here. So this quad that's aligned perfectly to the screen, and so of course we still keep this around. If you want to call this screen aligned quad or something like that, feel free to call it that. VS, feel free to call it that instead. I don't care. It's up to you what you want to call it. That is a little more descriptive if you did call it that instead. I have called it something like that in the past, and I didn't in this one. I just kept with the same old, but could be a little more descriptive. Get gray. Okay, so this one's kind of important. We're doing our dot product, and the reason we're doing our dot product is we have to deal with that gradient we were talking about earlier. The gradient here, remember we have these color gradients here, change between the different parts, and we need to determine based on the angle. Remember what dot product does great with. It does angle as well for determining whether or not it needs to go this way or not. For instance, 1 or 0, for instance, right? Another way to put it, okay, you have your camera and you're doing view fresh from culling. Is it within the range of the camera or not? So it should be drawn in the scene or not, right? So if it's in that range, it should be either in the camera or not in the camera. So, dot product works wonderfully for that. So that's why we have a dot product here. We're doing the color, and we're just doing a base gray here, a darker gray, for determining that one way or the other. And depending on how you manipulate this, depends on how you get your result. So, depends on what kind of result you get. You could even drive this if you wanted to, with a slider, possibly. So, I mean, that's a possibility if you wanted to change this. But the dark gray works out pretty good for this. Okay, so float 4 here, edge detect PS here. Open parentheses, and I'm sorry, this is a smearing operation. I should have mentioned this. So, here's our color, and then we're smearing it. We're saying X repeated over and over again for RGB here, and this is what's called smearing. And we just take that one value and we just repeat that one value across all the other values. We had done swizzling before, but I think I talked about smearing, but we've never had to use it in a particular instance. Well, cartoon shader edge detection, it makes a whole lot of sense for using it, because now all we have to do here is take this single color and smear it across the whole range here, and now we get smearing. So that's pretty cool. Note, if we wanted to, we could take the original image pass here before we did our smearing to it and everything, and then our color one, and multiply them at the end and get a result where we have the edge detect drawing on top of the 3D rendering. We could do something like that if we wanted to. I mean, there's lots of things you can do. You can stylize the stuff. You can even make it kind of sketchy looking on the color by manipulating it after the fact on the color pass here, so it looks like someone's kind of sloppy with the painting. And you can do that with several different processes and algorithms. The GPU Gems has some good routines for how to go about that. Some chapters on that to check out if you're really interested in that. Alright, so over here we have our flip 4, we have our edge detect PS. So this is the main shader here. This is where it has all the goodies. This is where all the knowledge actually occurs. And this is where we do our Sobel algorithm. So I'm just going to scroll on down some more. And let me just bring this up in size maybe, assuming I remember what it is. Oh, there it is. Alright, so I made it a little bit bigger, a little easier to read here. Okay, so we're going to do a float 4 here. I hope you don't mind. I'm just going to scroll on down. Float 4 here, edge detect PS, open parentheses, VS out, space, IN, comma, and then we're going to do our uniforms here. Uniform sampler 2D, scene sampler, comma. The reason why I did this technically is so you should do it for passing in. I don't normally do this. Normally I just don't bother passing these in because we can get away with it in FX Composer, but technically you should be passing in your Yes, they are const, they are uniforms, but they are. I'm forgetting. I just forgot what this is called. Um, I know it so much. I've said it in umpteen videos, and now I can't think. I do this all the time. All right. Well, anyways, you're going to take basically your UI control type variables here and annotations. You're going to take your annotations there. I finally remembered it. My gosh. You're going to take your annotations. I'm the most forgetful person. And then you're going to take your annotations and you're going to pass them in. Because technically you should. And if you're working with something like Scenics or something of that nature, you will definitely need to pass these in. That is a must type thing. So we can get away with it, not having to do it inside of FX Composer, but we should be passing them in. And this is how you pass them in. So, uniform here, space sampler 2D, space scene sampler is what's getting named as here. And I'm going to give it a little bit different name on that. Well, I don't have to. See, I can use it as scene sampler here. So this is kind of cool. Let me show you this real quick. Alright, so I can say scene sampler here, and then whatever gets passed in through the annotation, you probably go, well, that doesn't match our screen space sampler. It doesn't. But it gets, when we go in here to our fragment program, we're compiling it, we pass in screen space sampler, and that gets passed into the whole scene sampler. And it becomes your scene sampler. It just gets basically renamed, and you pass it into the function. And this becomes a local variable to this function. And that's what's happening. And it's just passing those values through. Same thing goes here for textile span and threshold. However, I do have them named that exactly. But if you don't like that, and you just want to keep it scene space sampler, you can do that too if you like, if you prefer. And then just use that throughout this whole code. But be aware, it does make it a little bit shorter if you just have scene sampler. But it's up to you whatever you want to do. Color. So because we're going to be returning a color, so this is going to be the output of this, which makes sense. Okay, so we're going to calculate the pixel range along X in textiles, just kind of like we did before over in the glow shader. When we did that, we're going to do it over here too. We're going to take our viewport size here, and we're going to take our textile span here for X. We're going to take our textile span, divide by viewport size, and that determines just how many pixels we're skipping at a time and point along this viewport as a percentage, more or less. And we have 0.0 here for our Y. And then we have our OY here, which is going to be our vertical range for pixels. And then so we're going to do 0.0 here, and then textile span divided by our viewport size vertically. And then that basically gives us a percentage amount of that span of textiles that we're manipulating. And that works out well. Okay, float UV here equals in.uv.xy. So the UVs of it, if you want, for UV. We could have done, oh well, XY works fine, but we could have done, I think, UV again. in.uv.uv. Anyways, doesn't matter. Move up along the Y direction for the pixel sampling. Yep, we're going to move it up 1. Because remember, if you remember, we hit up here, and moving up is going to be a subtraction algorithm, because this is going to be a 0, 0, 1, 1, like that. So if you subtract, it's going to take you up instead of going down. So we're going to deal with this top row first. So that moves us up into the upper range. Hold on, let me catch my bearings. Here we are. This moves us to our upper set of those pixels up here, so we're processing these here. And then after that, we're going to go down here and we're going to get our color here. And we're going to get a color here, CC, and it's going to be a text 2D scene sampler here, comma PP minus OX, because that'd be what? The left value. So which one are we looking up? We're looking up this one over here. Be your 0, 0 coordinate, if you will, of your textile basically the surrounding pixel that's above and to the left. Okay, so we grab that, and then we do a float G00 equals get gray here, open parentheses CC, close parentheses, semicolon. And what this does is this takes that takes that dot product there against the gray color vector here and to determine, where it falls in the gradient. And this will help us do our edge detection algorithm by putting it either one direction or another for the gradient with the dot product. So we're going to do the same thing again. Next pixel color we're going to sample, our textile if you want to call it that. It's going to be this one here. So it's going to be the 01. And we're going to grab that. And so yes, we have G01 here, get color, and we're going to pass in the CC. So we're passing in the pixel that we got for the above this one here. That pixel. Remember, this is the main pixel that we started with, and we're sampling the pixel above it. Alright. Going down from there, we say CC text 2D scene sampler here, and P plus OX. So what does that put us? Puts us over here in this other textile or pixel, if you want to call it. Okay? And we're going to get gray here, CC here, and this gives us a G here, O2. Here's our gray for our dot product into our, our dot product for determining that gradient. Alright, so it takes care of the entire top row here of this. Now remember, this is a textile span, so it doesn't have to necessarily be just one pixel over like that. It can be several pixels over, and then we're grabbing these particular ones based off of that and sampling. However, for just simplicity demonstration purposes, I'm just showing the surrounding pixels directly around this pixel. Okay. Now, let's switch over to a different setup. We are now going to go and choose the middle row. Tell you what, I'm going to break this up a bit so that it's easier to read for you guys. There we go. How about that? Now it's just a little bit easier to make sense of. Alright. So let's do the middle one here. So the middle one is going to be a PP here with the equal straight to the UV. That's going to place us directly at this position right here. So it puts us right at this pixel. So if we do PP minus OX here on the horizontal again, we're going to get placed over here. And we're processing it. We're grabbing that pixel, and then we're doing it times with our dot product in our gray value here, our dark gray. And so that's giving us our 10 gray, matrix value here for color matrix. Look up pixel color matrix, whatever you want to call it. Basically this one. And then we're going to get the center pixel. So this is going to be CC here, text 2D, sampler, PP. So of course that's simple. We just grab we don't have to do any manipulations to it. We just grab our pixel that we were predefined with. So that's simple enough. It's just going to be this pixel right here, which is 1, 1. And then we're going to pop it into our dark gray for our dot product modifier here and do it for determining the gradient. And then we're going to do again here, CC here, text 2D here, scene sampler, PP plus OX here. And that's going to move us over one color to this one here. And then we're going to do our dot gray, get gray again for the dot product, sorry. And then now we need to move down one row. So to move down one row, it's going to be plus. So this moves us vertically down and places us here. So that's what we're getting with this UV for the PP here. Now we just need to move over one to the left with that. So that puts us down here, which would be 20. And check it out, we have, after we're done grabbing that color, we get our G20 here equals get gray CC. And so that gives us our dot product of that color in the 20 spot. Of course, now we just say PP. We've already moved it down vertically, so we just say PP, and that's going to give us our color right there, that position right there. So that's our position 21. We're going to do our dot product gray lookup here as far as that goes. And then we're going to come back over here, and then we're going to add one over to move over to the next pixel to the right, which is this one here. And then we're going to do our dot product of that, the G22. Alright, so next we need to do our Sobel matrix operator for the horizontal operation. Now technically we could also do a vertical too, and have a vertical and a horizontal calculation. And so I went ahead and typed out what the vertical is too. Typically you're going to do both. We only did one direction, which means it's not going to draw it as cleanly or as pretty. You will get better results if you draw it both directions and have the combined values of the two, but it's faster if you only do one direction. So if you need speed, draw it in one direction and you're good to go for edge detection as far as that goes. So if we look at our Sobel algorithm, and this is where I was berating myself on this. Honestly, this should be vertical here when they're going horizontally across like this, and then this is supposed to be along the X. I got them mixed up thinking that this was the vertical and this was the horizontal, which you can see why I would get that mixed up, but I was wrong. So that shouldn't be H, that should be a V, and I need to switch the V's to H's, but essentially this is going along here. So 00, 01, 02, so on and so forth. Let's just go ahead and show that real quick. So 00, 01, 02, etc. So again, that's going to work here because this is what we have, 00, 01, 02 for vertical. Check it out. I'll prove it. See, -1, -2, -1. -1, -2, -1, right across the top like that. And then of course you're going to be at the bottom, and this is going to be like your 20, 21, 22 right here. And that should all be positive, right? So check it out. 02 is 1, 20 is 1, 21 is 2, and 22 is 1, which is exact match to this. So yes, this is the vertical setup, and yes, I wrote the wrong one here for it. So I need to change this to V's here all the way down the line. Alright, and then for these, I need to change those to H's. So the one below it is the one for horizontal here. And I really got to change the comments too because they're wrong now. But I noticed that after the fact, after I started recording, and kind of wanted to kick myself. After I noticed the algorithm, I was like, oh, I wrote the wrong one. Stupid me. Alright. All will be fixed here in 1 second. My apologies. Alright. I'm constantly fixing stuff. You guys are probably used to that by now. Seems like every time I do a video, I'm having to fix something. Anyhow. And then yes, I'll need to change all these over to V2, all the way down the line here. Just going to go over the horizontal one since the other one above is vertical. Alright, so just change all those to V's, so when you copy it down, it'll be V. But okay, so here's the vertical operation, and that's the one we're doing, but you know, we could also have done it horizontally or done both horizontal and vertical. And how do we do that? Well, it'd be this one here. So you'd say here you're going to do -1, 0, 1, -2, here 0, 2, -1, 0, 1. You're probably going, what? No, just hold up. It makes sense. It really does. I'll show you. Over here, so we have -1, -2, -1 going vertically down this matrix here for the horizontal. And the way that works here mathematically, think about it, this is 0, 0. This would be what? 1, 0, and this would be 2, 0. So that's what we're doing here. So check it out. Here's 0, 0. Here's 0, 1. And here's 0, 2. So -1, -2, -1 vertically. And then now we need to do the positives. So it's going to be 1, 2, and 1. And of course it's going to be what? It's going to be O2, it'd be 1, 2, and 2, 2. So let's check that out. So that's going to be O2, 1, 2, and 2, 2. So there we are. So that's 1, 2, and 1 going down vertically along this other edge of this matrix. And this gives you the horizontal version of it. So yes, we're only doing the vertical for now. Something else I want to point out about this algorithm, you'll notice it says times A here. So we got to multiply this by the source image. So how do we do that? Okay, well, we're going to be over here now, and we're going to multiply that times our good old gray. So that's going to be our source image in this case here. And our SX and our SY is going to be, we're going to initialize them to 0. We're going to create those two variables, and we're going to initialize them. And their initial values are 0 for obvious reasons. Alright, and then we need to start adding these together. Okay. So plus equals, here we go. So we're going to say the first gray times our value times our Sobel value here for our 0, 0. And basically our Sobel does the magic. And we just multiply this times our grays here, which again help put us in one direction or another with our gradient. So it makes this algorithm work really well for the edge detection when we manipulate our colors that way, one direction or the other. And the Sobel is going to do the edge detection now. So it's just going to go down the line here for our x's, for every gradient matrix, sorry, for every color matrix value for x. And we're just going to keep multiplying these different ones here based on the edge detection from Sobel, and let it work its magic for doing the edge detection, going all the way down the gradient. And that does it for all the x's. And essentially what that did is we just went through here each one, and we matched up the gray for this value here to go with the vertical Sobel algorithm for this matrix position here. So 0, 0 would be the same thing as 0, 0 here, because we're doing the vertical one. 0, 0 here, in this case -1. So hopefully that makes sense. So we're going to do those values multiplied together for that value of gray. And so we just do that for each part of this. So again, that would be, you know, this and this here, so on and so forth. And you just keep working your way on down through the whole matrix, color matrix here. And that's what we're doing here, moving ourselves down through the whole color matrix. And it just kind of lays out with the colors. So that's pretty cool. Alright. And then we're going to do the same thing for Y. So that exact same process I just said again for Y. So yes, we're going to go, you know, through each one of these. So 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 2, 1, and 2, 2, getting multiplied with their, you know, correlating color of gray variation here with the dot product of gray. So here we go. Bam, 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 bam. All the way down the matrix, color matrix. And there we go. So that takes care of Y. So now we have our Y and our X, right? So that's great. We need to do the distance formula as part of the Sobel. Alright. You might be going, you gotta be kidding me. Nope. No joke. No joke at all. So here's how we do this. If we look back over here, we have to do it for the magnitude here. So that's why we're doing our basically our distance formula. So as I mentioned here, it's the x coordinate is here defined as increasing in the right direction, and the y coordinate is defined as increasing in the down direction. At each point in the image, the resulting gradient approximations can be combined to give the gradient magnitude using the magnitude formula here. This is the formula. Using this information, we can calculate the opposite of the gradient's direction, which we don't have to do because we use the dot product. So, all right. So, but we do have to determine a threshold as to which way it is falling. So, we do our distance formula here, and then, and that's why we did square root of it. So, you know, sx times sx is the square root. Sorry, not square root. It's the to the power of 2 squared. sx squared and sy squared by multiplying by sy and then taking the square root of it, etc. All right, and we default to a result of 1, which would be white. And then if the distance is greater than the threshold, then we have an edge. And at which point we need to say result is equal to 0. And then we smear it. So for red, it's going to be X. For basically for green, it's going to be X. For Y, for blue, it's going to be X, and then alpha is also X. So this is red, green, blue, alpha, all smeared with the same value across the board. And that value is, of course, either going to be a 1 or a 0. So it's either going to be black or white completely all the way across. So say, for instance, the default result was that. We'd end up with, because of smearing, we'd end up with 1, 1, 1. So, so red would be 1, green would be 1, blue would be 1, and your alpha would be 1. If, however, the distance is greater than the threshold, then we end up with black, which is going to be 0, 0, 0, 0, which can be red is 0, green is 0, blue is 0, and alpha is 0, 2. And that's what you're getting here with that smearing technique. So we return quadruple X. And that essentially, and which returns a color value here, which matches up with our float here, 4, which is for the color output, which is cool. Alrighty. Now the only thing left to do is the technique. So none of this stuff should have changed. It's all the same right here. You may have fewer, however, passes to do. Not may, you will. Alright, so you only have one pass now. Alright, the only pass you have is the edge detect pass. So you need to change that there. Let me just squeeze this together a bit so you can see the comment I wrote. Alright. So I don't even think we changed that. I think that's the same from before. And then our pass here is edge detect pass. I just changed it to edge detect pass. I didn't really do anything different here. String script here, render color 0 equals nothing. Render tinsel target equals nothing. Draw buffer equals draw buffer. Draw equals buffer. My mistake, I'm sorry. Open curly brace here, depth enable test equals false, depth mask equals false, cold face enable equals false, depth enable, blend enable equals false, depth func here equals L equal, commented out. Vertex program equals compile VP30, here space main VS, open close parentheses, semicolon. And then fragment program equals compile FP30 here to edge detect PS here, open parentheses, screen space sampler, comma, textile span, comma, threshold, close parentheses, semicolon, curly brace, we're done. And again, we're just calling that edge detect. Again, this is our screen space quad, align quad. And then here we're doing our actual screen space calculation here for doing the edge detection, which is this right here. And we're passing in our screen space sampler so that way we can render to the screen. And here's our textile span, so we can determine how many pixels are going to be involved with this span here. And here's our threshold. And that, boys and girls, is how you do an edge detect Sobel algorithm shader. And that's the results you get from doing it. Alright, well, that covers edge detection, and with that, we're done. My name is Nate Nestler, and this is for Hyperactive Studios. Thank you very much.